Welcome back. In the last lecture we discussed syntax, and then in the next lecture we talked about semantics of propositional logic, and basically we are trying to cover a kind of crash course on propositional logic, because it is considered to be the most important thing for doing modal logics, because modal logics is considered to be an extension of classical logic. So in this lecture I will be talking about some of the important definitions that we have left it out, or we need to discuss it in somewhat more detail. They are logical consequence, consistency, satisfiability, etc., with some examples, and then I will quickly move on to one of the important methods that we will be using it in our course, that is, it is also considered to be a decision procedure method, which is called semantic tableaux method. So before that, let me begin with the definition of logical consequence. So the notation goes like this: if you take gamma as some set of formulas, and we use gamma for that particular kind of thing, which includes all the formulas that exist in our propositional logic, and A is any kind of propositional formula, and if you write gamma union A, it is set of all formulas together with a given formula. If that is the case, then gamma is said to be valid in any given model M. That means M satisfies gamma if and only if A is considered to be a logical consequence in that model M. It happens for every formula, that is A, in which exists in a given set of formulas gamma. Under all interpretations, a given formula is true, then it is considered to be a tautology, and all tautologies are considered to be valid formulas. So we denote this thing as M, any other letter A or something like that. And when do you say that gamma is considered to be, gamma means set of formulas that we have, that is considered to be satisfiable if and only if there exists a model M such that gamma is considered to be a logical consequence in that particular kind of model M, and it is refutable if and only if there exists a model M such that M gamma does not follow from M. Gamma is considered to be valid, which is denoted by gamma follows from something, or gamma follows from a model M. It happens for every model M, and it is considered to be unsatisfiable if it is not satisfiable at all. So basically we are talking about three important things: logical consequence, satisfiability, tautology, etc. Now why we stress a little bit on logical consequence? Because logical consequence occupies the central position in any logical system. So in classical logic we define logical consequence like this: if A be a formula and gamma is some set of formulas, and it happens in this way that if every model that validates gamma also validates whatever is there on the right hand side, that is A, then we say that gamma entails A, or A is a logical consequence of gamma, some set of formulas gamma. So A is considered to be a proposition. A is a set of formulas, or a formula is considered to be valid, which is written in this sense: A is a logical consequence, especially where A abbreviates this thing. We do not write anything on the left hand side, means A has to be obtained from some empty set. So that means it has to be a tautology. That means A does not require any kind of proof or anything like this. So it is considered to be a tautology. So in the same way, A is considered to be contradiction, especially when bot is a consequence of a given formulas A, and two formulas are said to be logically equivalent to each other, especially when B is a logical consequence of A, and the same way A is also a logical consequence of B. Or the other way around of saying is that A if and only if B has to be valid, or A if and only if B has to be a tautology. In classical logic we mean tautologies are considered to be valid formulas, and valid formulas are also considered to be tautologies. There are two other important things which you come across while doing any logic course. These are like this: soundness and completeness. Usually an argument can be valid, any given argument which is considered to be valid and it also has true premises, then it is considered to be a sound argument. If any given argument is valid but it has I mean one of the premises is considered to be false, then it is considered to be unsound argument as far as the argumentation is concerned. So in propositional logic, soundness is defined in this sense, particularly when whatever is proved is also considered to be true, then the system is considered to be sound, and a system is said to be consistent when all the usually we require this thing for this reason, that we want all the truths to be provable, and all the provable things are considered to be true or tautologies. So a proof 3D consequence relation, single turnstile, I have used two symbols, single turnstile and double turnstile, which is considered to be sound with respect to a semantic consequence relation, double turnstile, if and only if every possible set of premises, let us say P1, P2, P3 etc., and every possible conclusion Q, P1, P2, P3, from that Q follows, then Q is has to be a logical consequence of P1, P2, P3. So in a nutshell what it says is that if Q is deduced from gamma, it implies that Q has to be true, in Q has to be a logical consequence of gamma. So if A is deduced from gamma, then A is a semantic consequence of gamma, A is considered to be logical consequence of gamma. That means all provable things are considered to be true, and the completeness is like this: any proof 3D consequence relation single turnstile is considered to be complete with respect to a semantic consequence relation double turnstile, if and only if for every possible set of premises P1, P2, P3 etc., and every possible conclusion Q, and this Q has to be a semantic consequence of all these things P1, P2, P3. That means all these premises should make the conclusion true. It is like as good as saying that a given argument is valid, especially when it is impossible for the premises to be true and the conclusion to be false. If it happens in such a it happens in a way that your premises are true and the conclusion is false, the given argument is invalid. So this is also it can be viewed as, this can also be viewed as a relationship between syntax and semantics. In the syntax we talk about single turnstile, and semantics we talk about double turnstile. The relationship between these two, if you want to have a relationship between these two, we need to have soundness and completeness property. The basic idea is that whatever you have proved, I mean at the end of the day your proofs have to be true, and what all are considered to be truths in mathematics etc. have to have a proof. But this is a objectionable kind of thing that Kurt Gödel has come up with an interesting in his incompleteness theorems. He came up with this view that this cannot be the case. There are obvious truths, but they are not provable. Any given formal system which is following its own rules etc., but it cannot show that it is considered to be complete. That means all truths cannot be provable. So basic questions that we ask in the formal logic are these things: the soundness of the deductive system. Any given formal logical system we will be asking these questions: how sound it is, that means no provable formula has to be invalid, that means it has to be false. If something is proved, it has to be true. And the completeness of the deductive system, all valid formulas have to be provable. So we ask these important questions: that is the system consistent, is the system complete or sound, etc. These are the two important things. For logicians some other things are considered to be very important, that is consistency, completeness, etc. These two are considered to be the most important questions that logicians would be asking while working in any kind of logic. So there is another important thing which you need to note, all these things which you will be using it in the modal logic while discussing about the modal logic. So these are the terms that you come across even there also. When do you say that system is considered to be, a formal logical system is considered to be maximally consistent? A set of formulas, again gamma, is said to be maximally consistent if and only if it has to be consistent, and there is one more requirement, that is furthermore, given any formula A, this is an important requirement, that is this, that either A has to be provable or it has to be provable that not A is the case, but definitely not both the things. There are some logical systems, for example in the case of intuitionistic logic etc. Suppose if you cannot prove A, you cannot even prove not A, then you have to withdraw your fundamental principles of logic, one of the fundamental laws of logic, that is law of excluded middle. Law of excluded middle tells us that either P is the case or not P is the case, one excludes the other one. If you cannot prove P and you cannot prove even not P, there is no way in which you can validate this fundamental law of logic, that is law of excluded middle. So for the maximal consistency, either A has to be derivable or not A has to be the case, but it should not be the case that both are derivable from a given system. Maximally consistent sets are considered to be closed for derivability, that is given any maximally consistent set gamma and a given formula A is reduced from gamma implies that A has to be in that particular kind of set of formulas gamma. So why we talk about maximally consistent sets, because when we discuss about some of the concepts like possible worlds etc., in the case of modal logic we require these maximally consistent sets. A possible world there is defined in the sense that it is considered to be a maximally consistent set of sentences, they are considered to be possible worlds. In that context we need to know a little bit about maximal consistency. There is a supporting theorem, that is lemma, that is this, that if gamma is considered to be consistent, then there exists a gamma prime which is a superset of gamma, such that gamma prime is considered to be maximally consistent. I am just superficially I am talking about some of the important theorems. It is impossible to discuss all these things in 10-20 minutes like that. All these things require rigorous proofs etc. There are very interesting books in the related to introduction to logic. There you will find these theorems in greater. One best textbook is that Introduction to Mathematical Logic by Mendelssohn. That is a good starting point for understanding all these theorems and lemmas. So another important thing we need to notice is that gamma is said to be consistent if and only if it is satisfiable. That is also we need to note. There are some important properties of this entailment relation, and it is like this. I do not want to go into the details of all these things, but I will quickly switch on to the ninth one, that is gamma is said to be inconsistent if and only if you derive a contradiction from a given formula gamma, or otherwise it is said to be consistent. This is the one which we will be using it in our method, decision procedure method, it is the semantic tableaux method. Gamma is said to be consistent, then either A has to be gamma union A has to be the case, or gamma union not A has to be the case, but not definitely not both. If any system in which you derive both the things A and not B also, then that particular kind of system is considered to be inconsistent. And these are some of the important properties that any classical logic obeys in particular. So particularly there is one interesting property that we need to highlight here. So that is the monotonicity property, that is the second one. If A is a logical consequence of gamma, then you can add some further statements gamma and C, and from that also A follows. But in most of the cases it may not happen. For example, if you represent it like this in the case of conditional statements that we are going to talk about a little bit later. Suppose if you say that if there is sugar in the coffee, then it would be tasty. Obviously it is the case that sugar makes the coffee tasty, some of us. And then if you say that addition of new information, such as if there is a sugar in coffee and there is kerosene in coffee, then it would be tasty. So from A implies B, one of the logical consequence of A implies B is that A and C implies B, where C is considered to be the new information there. So that need not have to be the case in non-monotonic logics, where you need to drop this particular kind of thing which follows in classical logic, that is a monotonicity property. And there are a whole lot of logics that have emerged from this one. They come under the category of non-monotonic logics. Now let us get back to this important method, that is the semantic tableaux method. I will be highlighting this method because we will be using this method and we will be extending this method for modal operators etc. a little bit later. This is considered to be one of the important methods and easy to use, and this method is used to, it's like a decision procedure method with which you will be able to tell when a given propositional formula is a valid formula or a tautology, or when two formulas are said to be consistent to each other, or when two formulas are said to be logically equivalent to each other, many things which you can talk about it, or when two formulas are said to be, a formula is said to be satisfiable etc. So there are independently worked out by many the three important logicians. Everyone claims that the method is due to them only. So it started with Beth's works and it is further simplified by Hintikka in his modal sets, and Raymond Mullion also used. He is considered to be the founder of this particular kind of method. It does not matter who has come up with this method, but this method is very interesting. Here what we do is, what we essentially do is that given any formula which occurs in the propositional logic, we draw its corresponding tree diagram. A semantic tree which is called a semantic tree. Semantic tree is considered to be a device for displaying all the valuations under which a given set of formulas are considered to be true. The basic idea is that one of the important things which you need to note is that truth table method is also considered to be a decision procedure method, but it is going to be difficult for us to track all the rows of a truth table, especially when the number of variables increases. If there are 3 variables, you have 8 entries in the truth table, it is easy to manage, and the number increases, n is equal to 7 or 8, then we have 124 entries. It's very difficult to monitor those things. It is difficult for us, but a computer can do it easily, but it is difficult for us. So semantic tableaux method simplifies those things. So the basic idea here is that any inference is considered to be valid if and only if there exists no counter example. An argument is considered to be invalid if you have a counter example. Like, if your premises are true and the conclusion is false, then it is said to be an invalid kind of argument. So in the same way, suppose if you have a well formed formula something x, and if you deny the formula and it leads to contradiction, then that not x is considered to be unsatisfiable. That means x has to be satisfiable, x has to be valid argument. Unsatisfiability of not x guarantees that x is considered to be a valid argument. So we need to ensure us that if you want to show that x is valid, you have to show that not x is unsatisfiable. So these are some of the basic ideas that we will be using it here. The basic idea is that any invalid argument has true premises and a false conclusion. So this method involves a rule based construction of a counter example for a given inference. So what we do is we start with the negation of the formula, a given formula, and then we will construct tree diagram for the given formula, and then we will see if all the paths of that particular kind of tree closes or not. This whole thing is called as tabula, and this is also called tabula method. So when the tabula closes after denying the formula, that means not x is considered to be unsatisfiable, and that guarantees us that x is considered to be valid. It is a kind of reductio ad absurdum kind of method. Suppose if you are asked to show that x is the case, then you start with not x, and if not x leads to contradiction, then obviously that is not x is considered to be unsatisfiable, that means x has to be valid. Truth trees are considered to be one of the most efficient ways of checking the semantic properties of propositional formulas like truth, tautology, etc., validity, all these things, and in particular it gives very easy way of checking validity of sequence, especially when the number increases 4, 5, etc. Propositional variables increases, then it definitely helps us. The basic idea of truth trees is that they give a graphic way of, we usually say a picture says 1000 words, it displays as whether or not a set of formulas is said to be consistent or inconsistent, etc. So these are some of the rules that we use for constructing a tabula. As you see in this tabular rules, this tabula ends with atomic formulas. This is the most important thing which you need to note. For not P, it is same as not P. When you have a compound formula PRQ, it is a branch leading to PQ, and if you have P and Q and both P and Q have to be true, P implies Q has this particular kind of structure, not P or Q, and P if and only if Q is written as P and Q and either not P not Q. These are considered to be alpha rules. Now beta rules, exactly the negation of that one are like that. Not P is same as P, not of P or Q, you have to use De Morgan's laws, and not P and not Q. So that is why you have a trunk of a tree, and not of P and Q is not P not Q. So let us consider one example, and then we will see whether from P implies Q and R are not Q and not R, P follows or not. So here P is considered to be the conclusion. So it is like this, when P or Q R or not Q and then not R, and then whether P follows from this or not. So we want to check whether this P is a consequence of this or not. So in the semantic tableaux method, what you do is the first initial step is that you deny the conclusion. So this is what is denial of conclusion. So that means you are trying to construct a counter example here. So now what you do is you simplify these formulas with the help of semantic tree rules that we have. So now if you apply on this one, the tree diagram for this one, R not Q appears to be like this, R not Q. So it is a branch, so that is why it looks like this. So now you write the same bit of information here, R not Q. Now this is over, that is why we checked it, so that is why we put a tick mark here, over here. Now the formula left for us is this one. So this can be written like this, not P or Q. So this particular piece of information needs to be written under all open branches. So this branch is not yet closed. So this branch will be closed only when a literal and its negation occurs in that branch. Then you have to close the branch. So now the same bit of information you need to write here. So now we need to see whether this branch closes or not. So we have P implies Q, R or not Q, and we exhausted all the things. Then ultimately we have ended up with only atomic prepositions. So now this branch remains open because there is no way in which so this branch gets closed here because R and not R is here. So this gets closed here. This remains open. No, this also gets closed because R and not R is there. Now here we have not P not Q and all, so this branch remains open whereas this gets closed. So now what is the situation is that denial of the conclusion does not lead to contradiction. So that means we cannot surely say that X is considered to be a valid argument. So what essentially we are trying to do is here is that if you want to know that P is a logical consequence of given formulas, we are starting with the negation of the formula, and then we construct a tree diagram for these things, and then ultimately we are trying to see whether not X leads to contradiction or not. So there is a principle in logic which is considered to be reductio ad absurdum, which is like this: if from not X leads to some kind of contradiction, so then it should not be not X, but it should be not of X. So this is same as X1. So that ensures us that X is considered to be valid, but in this case it appears to be the case that after exhausting the tree rules here, I mean you ended up with atomic formulas, you did not come up with the branch closure. So branch closure suggests us that not x is unsatisfiable. If not x is unsatisfiable, then x is considered to be valid. So that means your counter example did not work there. So in the next lecture we will be talking about this semantic tableaux method in greater detail, and we will be using this semantic tableaux method for solving some of the important puzzles. These are some of the puzzles which are considered to be very interesting and exciting. Logic as a subject matter would be particularly interesting, especially when you study these puzzles, try to solve these puzzles by using the basic concepts of logic. And another thing which excites us is that paradoxes, Lias paradox, Barber's paradox, etc. So they are all valid arguments, but there is something wrong with those things. You can only show that they are considered to be unsound, or there can only be a resolution for these paradoxes, but otherwise they are considered to be valid kind of arguments. So in the next lecture we will be talking about semantic tableaux method and how we use it in solving two important puzzles. One is knights and knaves puzzles, and the second one is lady or tiger kind of problems. So these two problems are very interesting, exciting, and they are all cooked up by a famous logician, Raymond Smullyan, and we will be taking a few problems from that particular kind of these two books, and then we will be trying to solve those puzzles by using semantic tableaux method. Thank you.